How's everybody doing?
Yeah, pretty good.
We're back after yesterday. It's good to know that there weren't too many existential crises caused by yesterday, and I always have to be sure. It's like, all right, who's missing? Why are they missing?
I'm introduced. Everything I ever was told was a lie.
Yes.
There's lots of scary potassium use.
Yeah. Yeah, it's great at that.
Yeah.
So, last time we saw a bit about the holes in math, about the halting problem and the results of that halting problem with regards to the decidability problem in math, which is a very fun problem to actually go explore. We can conclude from this as well that if the halting problem were decidable, then we know that, or we could conclude that every recursively enumerable language would be recursive, which we also know to be false. But that would be a fun, if the halting problem were solvable, then that would also be true, which is an interesting, obviously false, but it would be an interesting conclusion if it were true. What we're going to start talking about today are some reductions to some undecidable problems. Have people seen NP-complete reductions possibly as something in some other class?
I've just heard P and NP, and I know that that's a thing. That's a thing.
Yeah. So NP-complete is I think I've mentioned it in here, but I'll summarize it again because you never hear this too many times. A class of algorithms where there is a polynomial time non-deterministic solution, but the best known solution deterministically is exponential. But if we ever were to find a polynomial time deterministic solution to one of those problems, then there is a polynomial time conversion between that problem and an entire class of algorithms, where if one of them could be solved in polynomial time, you solve that problem, then you convert that problem into the other problem also in polynomial time, and a polynomial time plus a polynomial time is a polynomial time. So you would have now solution to this entire class of algorithms because you could get there from the solution to this now polynomial time algorithm in polynomial time. And the way that that is proven or shown is through what we call a reduction. So a reduction is a polynomial time conversion algorithm between one algorithm and another algorithm, both of which are known to have exponential best time complexities. But outside of that, if we were to solve one of them, then we could solve all of them via the fact that they're all connected via kind of a minimum spanning tree of polynomial time edge conversions to a bunch of other algorithms. Why don't I just draw that out for visual purposes? So there are some problems, like we heard of the traveling salesman problem, that's one NP-complete problem. So there would be there's the traveling salesman problem. There'd be some polynomial time x to the n conversion algorithm where somehow we could turn the traveling salesman problem into the 3-SAT problem, which is another NP-complete problem. And then you could convert the 3-SAT problem into via some x to the n to some other problem. And the idea is that if we somehow could solve the traveling salesman problem in polynomial time, someone comes up with some solution to this, then we just apply this algorithm to that. And now getting here is solving that, which is polynomial time, plus this edge, which is polynomial time, which gives us a polynomial time solution to this. Since this is polynomial, this plus a polynomial time conversion to that problem means that that is solvable in polynomial time. So it spreads throughout this minimum spanning tree of a graph to every problem that is in this class of algorithms. And we would have polynomial time solutions for all of them. This includes the entire security of the internet, your banking. So if this ever happens, just get offline, go find a mountain, become a hermit. But that is what the P equals NP problem is trying to solve. If we could solve P equals NP, then we could have polynomial time solutions to all NP-complete algorithms. And that would break society, since now society is built around the fact that P is not equal to NP. And hey, you get $1 million payout for that, just in time for the entire society to crash and the dollar to become worthless. So maybe there's an argument to not solving the problem. But we can use the same concept of a reduction to talk about undecidable problems. If we can convert one undecidable problem into another undecidable problem, or what we think is an undecidable problem, we could say, here's a reduction to show that if we could solve this particular problem, then we could solve the halting problem. And since we know we can't solve the halting problem, then we know that we can't solve the query problem, because we obviously now have a proof for that we cannot solve the halting problem. So yes, we can determine the decidability of a problem based on a known undecidable problem, or vice versa. Then we know the query problem is also undecidable. If it were decidable, we'd have an algorithm to decide an undecidable problem, which is obviously not possible. So we can use this to discover more and more undecidable problems. And then as we have new query problems, we can create connections between this new problem and more problems that we have proven to be undecidable. So that class of algorithms is always growing as more and more of these problems are found and tied to known undecidable problems, creating a new minimum spanning tree. Rather than solvability, it's kind of unsolvability. It's proofs that we could not actually decide that problem. So let's give you an example. We want to answer the question whether some Turing machine enters a particular internal state when M is applied to an input string. All we have to do now is find some kind of logical connection between this problem. We need to manipulate it into the halting problem, which we just do if we assume that that internal state is the accepting state. That says we would halt and accept. So just to reduce it to the halting problem, assume there exists an algorithm that solves what we're going to call as the state entry problem. We modify M such that M is M proof from the halting problem, such that M proof halts in state Q if and only if M halts. Then we apply the state entry algorithm. And if M proof answers yes, that Q is entered, then M proof halts. And if M proof answers no, Q is not entered, then M proof does not halt. And what we have found is that now this modified algorithm solves the halting problem. And the only thing that we did, again, a proof by contradiction, is that we assumed that algorithm A existed. We used perfect logic between there and the end result of we solved the halting problem. So the only reasonable conclusion from this is that algorithm A cannot exist. If it did exist, we could use it to solve the halting problem. We have a proof that the halting problem is impossible. Therefore, A is impossible. We can use this as well for recursively enumerable languages. So we know for recursively enumerable languages, there is no membership algorithm. That means that we can't answer yes and no. We can only answer one. We can answer yes, but not no. It's interesting how little we can state about recursively enumerable languages. A lot of the simple questions we could ask about recursively enumerable languages are undecidable. One thing that we saw a couple days ago was that unrestricted grammars were equivalent to a recursively enumerable language. Recall that unrestricted grammars said that we can have terminals and non-terminals on the left-hand side in addition to the right-hand side of that grammar. So let's start by assuming we have such an unrestricted grammar, and we can find from there, we can ask the question of, is that language empty? Are there 0 strings in that language? And it turns out that that problem is undecidable. Does that make sense? As soon as we discover a string in a language, we halt and say, great, it's not empty. But as long as we have generated all possible strings that are one step away and found that there are 0, 2 steps away from the starting state, found that there are 0, 3 steps away from the starting state, found that there are 0, 4 steps away from the starting state, found that there are 0, are there going to continue to be 0? It's hard to know if after some number of steps, you would derive the first string in the language. It may just be that this grammar is very complicated and requires a lot of intermediate steps in order to generate any string in that language. How would we know from just looking at the grammar? Something that you have to simulate.
And I
Yeah.
mean, it's possible in specific cases, right? Like if you had a production where it's like AB converts to BA and S converts to AB, and those are your only productions, it's like, okay, well, yeah, sure, that'll just, you can never reduce it on a single
Right.
string.
Yeah, you have to have some kind of logic, and this is very similar to the halting problem, where if you're looking at a single algorithm and looking for a single rule within that, like look for any loop that says while true. And if there's a loop that says while true, scan for a break or a system exit 0 or something that actually terminates that loop and terminates the program from there. If you don't see that, then there is no way that loop will ever terminate. But is that every possible infinite loop that you could find in a program?
Right.
There are go-tos, there are loops that just won't terminate. There are loops that you could write that if your accounting variable is mod 2 is 0 is even, then you increment something, else decrement something, and it will just go up and down and up and down and up and down. Even though there is a termination condition, the counting variable will get to that termination condition. There are an infinite number of mathematical paths to create something that won't terminate. So you have no hope of being able to analyze and catch all of them. So yeah, you could look for a particular type of grammar loop. That means that it wouldn't generate a string from there. But to be able to do that in general, for every possible mathematical way to loop a grammar, to loop an unrestricted grammar, it's not possible. That's a great point, though, that yes, you could analyze it and find some evidence for a particular grammar. So here is one question you can't answer in general. Assume we have a Turing machine. Is the language accepted by M finite? This is also undecidable. Are there a finite number of strings in the language accepted by a particular Turing machine? If the answer is yes, we will halt and have found them all. If the answer is no, we will keep generating new ones and keep generating new ones and keep generating new ones. Are we going to reach a stopping point? At any particular point in that process, it's impossible to tell until that process is finished. And the process will only finish if it's finite. Therefore, it's recursively enumerable, and we can't answer the question, is the language finite in general? You cannot write an algorithm that will do that. You can use intuition and look over a grammar and try to determine, is this finite, yes or no? But it's going to rely on that intuition or some kind of larger scale analysis of that grammar. And you won't be able to use the same process for every single grammar. Assume we have a Turing machine over a small alphabet. Are there 2 strings in the language accepted by the Turing machine that are the same length? If we can find those 2 strings, great. If we have generated 10,000 strings and they're all of different length, is the next generation going to be a different length, or will it be one of the existing lengths? Impossible to know in the middle of that execution. Once you find it, you know. If you haven't found it yet, you don't know. It's ambiguous. Are you going to find one eventually? Undecidable, reduction to the halting problem. So I don't, in an undergraduate course, care to go too much into the detail of how those reductions work. It's more important that we have that conclusion that that is how we show this. And that way, if for some reason in your future, you stumble upon something that you would need to show with a reduction, or just knowledge in general of how what that limit of computability is, if you have some way of determining, well, this question that I'm being asked in this setting involves the use of a recursively enumerable language. It's useful to think about, what can I actually answer about this? Or if you are asked to do something like, write a program to determine one of these very simple problems, your manager might say something like, well, it's such a simple idea. And you could show them a theoretical idea, and it just says, this is not possible. You asked me to do something easy, but it's actually impossible. Here is how I would go show that. And then they say, nerd, and demote you. Question?
Prove is a reduction in the halting problem basically just means that, or it's any problem. Basically what it means is if you start a proof, you're gonna wind up at that problem.
It means that that is the destination of it.
Yeah.
Yeah, you would say, if we can determine this problem or decide this problem, then we could decide the halting
So
problem.
the same problem, look at the core.
Yeah, there's a polynomial time conversion algorithm between them, or there exists, in this case, it doesn't even need to be polynomial times. There exists a conversion algorithm between them. That by solving this, I could then construct the halting problem out of this problem. And if I could solve this, then I could solve the halting problem. Yeah, so it's worth talking about the practicality of this, because it seems like, you know, maybe if I'm lucky, I'll experience this once in my career and get to shove this in my manager's face, that I took a theoretical computer science course and I know what I'm talking about and they don't. But it's certainly cumbersome to work with and not what everyone wants to be doing necessarily, but it turns out that we can make some statements, determine some things about context-free languages, and learn some things about compilers from these reductions, about what a compiler can and can't do as well. And it's fun to think about because reductions from the halting problem have some middle ground for these results as well. And I'll give you an example of this called the post-correspondence problem, which is a much more useful problem in computer science. So what you're given two sequences of n strings over a particular input alphabet. Post-correspondence says, is there an arrangement of each set of strings that produce the same output string? Giving you an example. I give you W1 is 1, 1, W2 is 1, 0, 0, W3 is 1, 1, 1. B1 is 1, 1, 1, B2 is 0, 0, 1, and B3 is 1, 1. The question is there a way to tile these in such a way that you have the same output string, but they're made up of concatenations of everything from W and everything from B? So here is a solution to this, that 1, 1, 1, 0, 0, 1, 1, 1 is a solution to this. The question I would have for you is this problem decidable? And the answer is not for all possible string sets. Note that in this case, there are only 2 queries, but what if there grow to be more than 2 queries? Is there a way for all 40 of these string sets to produce the same? You might think of it as just a combinatorics problem at that point, but it turns out to not necessarily be possible. So we modify the problem where we have 2 initial strings that must start the post-correspondence problem. Now we say W1 is the beginning of 1 and V1 is the beginning as well. Is there a way to construct the post-correspondence problem here? And this is a reduction to allow us to talk about, well, if W1 and V1 are the starting states of 2 grammars to start a derivation, derivation becomes an application of the post-correspondence problem. So we can start coming up with some undecidable problems for context-free languages and map those back onto the halting problem or the post-correspondence problem. Once we have proven that the post-correspondence problem is undecidable for all string sets, we can start reducing to the post-correspondence problem. This is very similar in the Veritasium video to the Wang tiles tiling the plane. I don't know if other people drew that conclusion as well, but it's very much like you have a plane to tile made up of digits. And it's just a one-dimensional plane instead of a two-dimensional plane, where the blocks are the start and end versus the sliding of the top, bottom, left and right. So very similar idea between this problem and the wing tiles problem, just one dimension different. So let's see what kinds of claims we can make about context-free languages that might determine whether we can do something with a compiler or not. As an example, this one we've already shown. There is no algorithm for deciding whether a context-free grammar is ambiguous. I think we didn't necessarily show that, but we talked about it. How in order to find that ambiguity, we have to, it's easy to prove that they are ambiguous because you just construct for one possible string, two different paths through the grammar that produce that string. Once you've done that, then it is ambiguous. But how would you show that a context-free grammar is not ambiguous? That there is no such string that has two different paths through that. You could show it for all strings of length 0, all strings of length 1, all strings of length 2, all strings of length 3, but if there are an infinite number of strings in the grammar, that process will never terminate. And because of that, you'll never be able to answer no, that the grammar is not ambiguous. So we can use this and show that it reduces down to the post-correspondence problem. Other interesting derivations. No algorithm for deciding whether the intersection of languages defined by two arbitrary context-free grammars is the empty set, meaning that they don't share any strings in common. We have two context-free grammars. Do they share nothing in common? As soon as we find a string that they share in common, great, there's some overlap. But if we've gone through thousands or millions of iterations of these context-free grammars and generated completely different subsets of strings, does that mean that they are completely different grammars that don't generate the same string, or have we just not looked deep enough yet? These are infinite languages, so we're never going to finish going over either one. If we haven't found one yet, it's ambiguous between we will find one later and we will never find one, no matter how long you've been searching. Once again, a reduction to the post-correspondence problem. You can use other reduction proofs to show all of the following ideas. There are quite a few more conclusions we can draw here. If we have two grammars, G1 and G2, that are both context-free, do they generate the same language, exactly the same language? As soon as you find a difference between them, the answer is no. But you keep looking forever and you keep finding that there is overlap between them and overlap between them and overlap between them. Is one language defined by a grammar a subset of another language defined by a grammar? That is also undecidable. If a grammar is context-free, is the language of that grammar regular? If the answer is yes, that's great. But just going from a grammar itself, that's a strange result. If we have a context-free grammar and a regular grammar, is the regular grammar a subset of the context-free grammar? And if we have a context-free grammar and a regular grammar, is the intersection of that the empty set? All of those are undecidable. Any questions or thoughts on any of those results? These end up being really important for compiler construction, because if we could do some of these things, then we could design very efficient compilers for certain components of the translation process of a compiler. But because we can't, we have to find workarounds.
Yeah, I think, once again, just to make sure I'm understanding, so we're talking about decidability. This is in the most general context of like, you're just given any random definition of a grammar, and then you have to have an algorithm that can work whatever you give it. Okay.
Yeah, so obviously something like taking the third bullet point, if you have a context-free grammar, is the language of that regular? Yes, all you have to do is draw a DFA for it and you're done. But is there a process in general to translate from a context-free grammar to determining whether you can make a DFA for that, yes or no?
Right.
And that process is impossible.
Or if you came up with an algorithm and it like sometimes terminates and produces the DFA, but sometimes just goes forever, that also doesn't
Right.
solve the.
Yeah, is the forever just, we haven't come up with enough memory to represent that DFA yet,
Okay.
yes or no?
Yeah. Okay.
Because a DFA could have an arbitrarily large finite amount of memory, and this process would continue to look through more and more and more memories. Can we make a DFA with 2 states, a DFA with 3 states? What are all the options? What are DFAs with 4 states? All the options. And you just go through every possible DFA construction and check whether that DFA perfectly maps onto that grammar. But you would never terminate. If you did terminate after a million states, I could generate a grammar that can't be solved, a regular language that with a context-free grammar can't be solved with fewer than 1,000,001 states, more than that. So again, you would never know for sure with that same algorithm. Questions on that? We said the second half of this class is very theoretical. We'll bring it back to reality by the very end. One thing we haven't really discussed at all is the efficiency of Turing machines, because we've kind of been using it as a theoretical concept of we don't really care how inefficient it is, we just care about what's possible and what's not. And the entirety of algorithm analysis says that in the real world, efficiency is very important. So what can we say about the efficiency of Turing machines, or how can we map efficiency onto Turing machine ideas in ways that matter? So as we've seen with different algorithms, you can solve problems in multiple ways, and the efficiency of multiple of those different solutions can be in different orders of magnitude from each other based on the size of the input. It's the same with Turing machine programs. You can solve the same problem in different ways with different Turing machine programs, and they will have different associated complexities. So efficiency of deciding A to the N, B to the N on a single tape. You can, with 2 N moves, match a single A with a B. And since you need to map every A with every B, then you get a quadratic order. If we're able to do this on a 2-tape Turing machine, rather than a 1-tape Turing machine, then you just put all the A's on the first tape and all the B's on the second tape, and then on a single pass, you could map an A with a B, A with a B, A with a B, A with a B. And if you see blank blank at the end of that, not A blank or blank B, then you would know it's in A to the N, B to the N. So we could even assume the entire string starts on tape 1, but copy all of the A's onto tape 2 as you do this. So as you go past all of the A's, you're writing A's on tape 2. Then when you hit the B's, you're gonna go backwards and continue reading B's on tape 1 and reading A's backwards on tape 1. And then you would see, if you go to blank blank, then you get to that point. So we have a linear time algorithm for computing A to the N, B to the N, assuming we had access to a second tape. And all that changed was the memory layout of the Turing machine. And it never changes the solvability of the problem, but the layout of your Turing machine can vastly increase or decrease the associated complexity of solving an underlying problem. And this makes a lot of sense when we think about parallelism, when we think about having access to multiple CPUs and the ability to fork into a limited number of threads. We now have the ability to do some non-determinism with that. The 2-tape Turing machine is actually emulating non-determinism. Does that make sense? It doesn't matter how long it is, you just write all of the A's, and then you guess where the middle of the string is, which is when you see that first B, we then move back. But where that fork happens is when we see that, and the second tape is allowing you to go backwards as soon as you see that first B, whether that is at the end of the second character or third character or fifth character. You have a second process that's ready and waiting to map B's to A's once we finish reading the A's. but that caps with the second CPU core. If we needed a third one for some reason, a two-tape Turing machine wouldn't be able to handle that class of problems. So parallelism allows us to handle small types of non-determinism, or small amounts of non-determinism. Obviously very limited with the power of those CPU cores and scheduling, but we can do it nonetheless. So all of this speaks into kind of the electrical engineering design of computer components. Can we design things in a way that we can reduce the complexity of common algorithms by allowing how it operates underneath the hood to be more efficient? That's a whole other rabbit hole that we're just not going to go into this class, which is the associated complexity that is allowed from different hardware configurations.
I just started messing with the TMA that were just amazing.
Yeah,
We had a co-processor for like moving stuff to and from peripherals and memory.
yeah,
It takes no processor time. It's
Yeah.
completely separate.
yeah,
Just give it instructions and it goes.
yeah. That's a very deep rabbit hole. It's a very interesting rabbit hole to go down. We just have so much more to do. So that's the end of this deck. We're getting close to the end. That's the end right there. We have 4 more slide decks. So we finally, after all of this, get to start talking about compilers.
Yay.
Hot diggity. Yeah, so we've now finally covered enough theoretical background to be able to have a conversation about compilers. Now, I could have introduced this on week 1, but to really understand how these work underneath the hood, we have to have had this level of background and understanding of how state machines work, different classes of languages, because with that level of understanding, it's much easier to see exactly how compilers work. So the name of the class, why we took the class. So we've talked about it a bit, but anyone want to summarize the 1 or 2 sentence summary of what a compiler is and what it does?
I mean, it's kind of like the wife I don't have. It just tells me what I did wrong.
I'm gonna say it's a program that turns your code into errors.
Yeah.
It's something that can take whatever grammar and syntax that we as programmers write, and then we convert it into stuff that the machine can understand into assembly and machine code.
Yeah, yeah, so it's a translation program. It's like Google Translate or any other translation program that takes as input one language and spits as output another language. And the goal of a compiler is to translate between the high-level language that we as programmers write and read and what a machine writes and reads. Yeah.
It's totally off topic. Do you think that actual language, like human language translation programs work on fundamental similarities to compilers?
Depends on the language.
Yeah.
So if you look at the actual language grammar constructs, there are so many special rules to that it makes it very difficult, and it's more successful if you use something that looks more like a deep net as opposed to an actual state machine. But when you're looking at a logical language to a logical language, there is always a one-to-one translation.
Wow, unless they have a word we don't or something.
Yeah, in a logical way.
Oh, logical, yes.
Yeah, so you're converting mathematical ideas or logical ideas. In language, that's not necessarily true. So you need to have some amount of analysis to that to try to find the best or closest fit to a particular meaning. And that's the difficulty in spoken language or written language. But in logical language, it's just how does this language represent that logic? How does this language represent that logic? Can we write a general translation algorithm that converts the input into the output? So high-level languages, great for humans, gibberish to a computer. Low-level languages, easier for a computer, gibberish to humans. We've all taken an assembly course at this point, most likely, so If I just showed you an x86 program and said, what does this do? That's gonna take a little while. If I showed you machine code, it would take even longer. But you feed that to a machine and it instantly does what the program says to do. So do note that assembly language is not directly readable by a CPU. We still need an assembler to convert that into machine code, which can be run. But it is a middle ground of something that if you write an assembler, then you only need one assembler per architecture. And so you can hard code that assembler. And then the only thing that you need to write is the compiler down into that middle ground assembly language. So the reason assembly languages exist is for exactly that reason. What part of this translation is not going to change and does change across architecture, but doesn't change. You want to get that as close to the high level language as you can so that there's less conversion to do when you do compile down to that assembly. There's less work that a new compiler has to be able to do to translate down into that assembly language. So machine code is great. It's platform dependent. It's unfortunate that that's true, but if you've ever tried running an EXE on a Mac system, on a Linux system, that obviously won't work because it has been compiled and assembled for that architecture. And if you don't have that architecture, then it won't work. There's also bytecode, so Java compiles down into bytecode, very similar to an assembly language, but bytecode is a middle ground, and then the bytecode is platform independent. So that allows us to use the same compiler down into that bytecode, and then the bytecode has the ability to be run on different architectures. So run on a virtual machine, and that virtual machine has its own architecture. And so the input and output from that virtual machine is then converted back and forth between the associated output that it needs on that machine, which is why Java is so good as a platform independent language. It's really the only reason I would use Java in today's day and age, just to make something that easily will run on any particular platform. But other than that, there's probably a better choice out there. But in general, how does the process work? Think about that from everything you know about programming. What would the associated steps be if the goal is to translate something like Java into something that, like bytecode, can be run across systems? Any guesses as to what the actual steps of that process are? Where would you start? You start with a Java program as input. What do you do to that Java program to be able to start this process?
Start with the outermost brackets.
Do we go character by character? I see an A, what does that mean?
I go keyword by keyword, probably.
Keyword, so yeah, so keywords work, some keywords in Java are defined like class and public and while. But what happens when I see a variable name or a value or an operator? Plus equals is two characters, but is a single operator. It's very similar to the idea of a keyword, but we call it something else.
Token?
We call it a token. It is tokenizing. That is the first step. So we're going to take this stream of characters and we're going to turn them into the equivalent of English words, where we character by character, the first character of the word character is C, which independently has a meaning as a letter, but not as a word. When you combine those characters together, you get words, and those words have meaning, but only within a particular context. So the first thing is to scan the characters and create tokens. Those tokens are the equivalent of words. Once we have those tokens, so now instead of a stream of characters, it's a stream of tokens. What do we want to do to those tokens?
You want to try to build them into a parse tree, right?
Yeah.
Applying a grammar.
Yes, so we would use the grammar of the language at that point to be able to answer yes or no. Is this stream of tokens syntactically correct in this language? So imagine we've built that parse tree. Imagine that we've created this, we've matched to this grammar, and the answer is yes. This program is syntactically correct. What's the next step?
Coming up with the semantic meaning of like, you have this parse tree. So what does it mean in terms of the operations that should be performed? Which I think
Yeah.
involves usually labeling nodes of the parse tree. Is like,
Yes.
what class do they fall into?
Yes, we call that a type checker.
Okay, yeah.
Yeah, that's exactly right. I mean, to come up with semantic meaning, we need to make sure that this syntactically correct program is constructed in a way that, at least at compile time, we know isn't going to have a compilation error because we're trying to map a string to a double or some other kind of type clash. So this modifies the parse tree. I'll just generate this at this point. This modifies the parse tree that was fed into the type checker, and that generates intermediate code, what is going to be called intermediate code. This intermediate code may be suboptimally written. So we feed this into a code optimizer that is going to attempt to, with some level of efficiency, turn the running time of what you wrote into something that is faster or better, especially with respect to what we know about how that intermediate assembly language or bytecode is run. Once we have fed it through a code optimizer, then we go through the generator that generates the associated output language. And from there, we have our machine code, our assembly language, our bytecode, whatever the output language is from this compiler. So these are the steps of a compiler. And you can almost write them all independently of each other, which is, they're kind of like methods in a program. One takes as input what you can assume the other steps have done, and the goal is a small piece of that conversion, or a check, or an optimization, or something of the sort. So what's great about compilers is, especially in a 10-week course like this, I can assign you one part of this and not horribly overwhelm you by asking you to write an entire compiler. So we're going to hone in on the parsing step, as we already have with CYK. And the second programming project is going to be a more efficient parser for grammars that can be more efficiently parsed than CYK. But we'll talk about each one of these steps in a bit more detail so that you can get a sense of exactly a visual of what that looks like before we go do that. So the rest of this class will have a small lecture on each of these steps, and then a deep dive into the parsing step, because that is very frequently the hardest step of this. Tokenizing in general is just finding the associated words. This step is very important, but also is probably the easiest step in there. So a token is just characters surrounded by white space. So all we have to do now is scan character by character and turn this into a stream of tokens rather than a stream of characters. Each token, as we do this, is assigned a type. We can tell from that token whether it is an integer, a float, a keyword, a variable, an operator, some class of token based on what we would expect from that grammar. And of course, if the user hates white space, then we see a single token and we need some kind of additional analysis to break apart strings into their associated tokens. So sometimes when someone's writing a for loop, for instance, they don't put white space in between the tokens in between and the associated for an immediate left parent, it should be two tokens. Start typing without a space after that parent, that gets shoved together. Anything shoved between the semicolons in a for loop, those are all tokens that would need to be split apart. So yeah, if someone does something like this is many tokens embedded in one. for left parent I equals 0, semicolon, I less than 10, that's a single token. Semicolon, I plus plus, that's one token. Sorry, I is 1, plus plus is 1. Right parent, open curly brace. So quite a few tokens embedded in that one between white space. So as we do this, we assign token type tuples and we store those into a list. We pass that list onto the parser. Tokens and types here.
Some
Types,
variable.
yep.
Yeah.
Next one. Equals is an operator, or the assignment operator, to be specific. Total is a variable, plus is an operator, 10 is an integer constant. And that has nice syntactic meaning, but note that green if 6.587 is syntactically correct and semantically useless. So green is a variable, if is a keyword, 6.5 is a float constant, and 87 is an integer constant. Has absolutely no meaning.
Bet it would run in JavaScript.
What doesn't run in JavaScript?
I don't know.
So how would we go do this? How could one implement a scanner? What's beautiful is the scanning process maps directly to a DFA, where we read character by character, and at the end of that, you could have different final states, depending on the final state that you reach. There are certain ones for recognizing keywords. You would just do a particular analysis of that, run it through the keyword DFA. And if you ended a final state, then that's a keyword. If not, then it's not a keyword. So we could use a DFA to recognize tokens and token types as well. So you could, for instance, in Java, we can't have a variable that starts with the character equals. The equals green is not a valid variable name because it's ambiguous with some variable named green because something equals green plus something else. So we could look at equals green at that point to determine that that is either two tokens or it is not a valid token. So final states recognize different tokens, read each token until we get a set of tokens that's identified as some kind of label of interest. Once it's done, once it reaches that final state, it says this is a token. The final state tells you which type it was. So you could construct a DFA for token analysis. And you could build a regular expression for each valid token as you do that. And it allows easy access. So it turns out that studying regular languages, we did at the very beginning of this, was all preparation for the ability to implement a scanner for tokens. For each token, compare it to each possible regular expression until you find a match. This seems like a nice natural place to stop before we go into parsing, which we've talked about to some extent, but yeah.
Told my nephew that I was learning how to write code in Java. He thought that Notch, the guy that made Minecraft, invented Java.
Cute.
So that was my little tidbit for the launch.
That's funny.
He made more than the people who did.
Yeah. You can say that the Oracle of Delphi is the one who invented Java. Any other questions or thoughts as we pack up and get ready? Office hours in an hour to talk about anything ongoing.
No questions.
All right, we'll pick this back up tomorrow and talk about parsing.